Welcome back. Previously, we outlined how Robert Mayer took data available in the scientific community and used it to illustrate what is now one of the bedrock principles in thermodynamics. Energy is neither created nor destroyed. Crucially, he showed that work and heat were related to each other and that one may be converted into the other through an engine or through physiological processes in living things. Yet, if you were to ask a current scientist who demonstrated that work and heat were both forms of energy, you would probably not get Robert Mayer's name as a first response. More likely, you'd hear the name James Joule. To this day, Joule seems to get more recognition for discovering what is now known as the First Law of Thermodynamics. There's even an energy unit, the Joule, named after him. After all, no one uses the Mayer to discuss energy quantities. In the 1850s, this frustrated Mayer to no end, as he had published the idea a little before Joule. We'll discuss why Joule seems to get more credit nowadays a little later, but first, we need to explore why he gets credit at all. James Prescott Joule was born to a family of brewers in Lancashire, England on Christmas Eve, 1818. As an adult, after taking over the family business, he started his scientific inquiries while exploring ways to improve mechanical processes in the brewery. He discovered a relationship between electrical resistance and current that was responsible for the heat generated in an electrical circuit, a phenomenon that to this day is called Joule heating. He also went on to demonstrate that a specific amount of work from an electromagnet spinning in a container of water corresponds to an equivalent amount of heat associated with raising the temperature of the water. This work was published in 1843, right about the time that Mayer was introducing his findings. Unfortunately, the British scientific community was not impressed, and Joule's work was largely ignored. What Joule did next was to design an apparatus that illustrated the link between mechanical work and heat in a way that was more direct and visual than electromagnetic force. He constructed a device consisting of a metal container fitted with a set of spinning paddles inside. The paddles were connected to a spindle, and that spindle was connected to a set of corded weights on a pulley. The weights were designed to drop a specific distance toward the ground. Knowing the acceleration of gravity, the mass of the weight, and the distance dropped, the mechanical work done could be calculated in a way obvious to all. As the weights dropped, the cord would spin the spindle, turning the paddles inside the container. If the container were filled with water, the paddles would then transfer the energy from the falling weights to the water, raising the water temperature that was measured by a thermometer. Thus, an amount of heat equal to the work done would be transferred to the water by the falling weights. It was a quantitative experiment, and the results were immediate. Joule created his device, reported his first results in 1845, and by 1850, he had refined his experiment to the point where his measurement of the specific heat capacity of water was nearly identical to the value we use today. The experiment was a success and was reported in his now famous paper on the mechanical equivalent of heat. We have the ability to reproduce Joule's experiment with some surprisingly simple equipment, using a motor rather than weights and pulleys. Let's go to the lab and take a look. So in this experiment, we're going to duplicate, somewhat, Joule's experiment using a household blender.
If you think about it, a blender is very similar to Joule's apparatus. It has a set of paddles attached to a spindle within a container. The spindle is attached to a source of work. Only this time, instead of a weight on a rope, the source of work is an electric motor. We can spin the motor for an amount of time to generate a specific amount of energy, which is transferred to the water in the blender. And we can introduce a lot more energy in a much shorter time than we could with a weight on a rope. First, we've got 1 liter of water in the pitcher, and then we'll check the initial temperature of that water, which is 18.06 degrees Celsius. Now let's run the blender for 60 seconds and see how much heat that introduces to the water. You can see that the reading on the temperature probe is increasing during the course of the experiment. The temperature increase indicates the introduction of heat into the water coming from the spinning of the blender blades. So we finished, and we can look at the overall change in temperature, and from there, calculate the heat that went into the water. We can also use the current, the voltage, and the operation time on the blender to figure out the work done by the motor. And using these two numbers, we can calculate how much of our motor's work turned into heat in the blender. Interestingly, it turns out the efficiency of converting our energy isn't all that good. Only about 1/4 of our work is transferred into heat. Where are we losing the efficiency of converting work into heat? Well, we lose efficiency when the motor heats up on its own instead of heating the water through the blades. And we can feel here that the motor did get a little warm. Also, some of the motor's energy goes into spinning a cooling fan in its base. And we even lose some heat generated when it passes through the glass and heats the surrounding air. If we really wanted a perfect efficiency of converting the work into heat, we'd need to design a motor that minimized all the other heating losses. Actually, we'd probably be better off using Joule's design with the ropes and the weights and the pulleys. But a blender isn't designed to convert work into heat. It's designed to chop food or mix smoothies. So you don't really need an efficient process when all you want to do is prepare food.
At any rate, we've found that Joule's tie between work and heat is valid. Yet, even Joule's improved experiment initially met with little fanfare. Those who noted his work at all were skeptical of his results, even though his process was much more direct in its measurement approach than what he or Mayer had earlier reported. Once again, we can attribute some of the skepticism to Dr. Kuhn's paradigm idea we talked about at the beginning of this series. Remember, in the 1840s, most scientists were still working under a paradigm that used the caloric model in its framework. If you were touting an idea that was outside this paradigm, the idea that heat wasn't tied to an actual substance but was part of this non-material thing we call energy, well, you had your work cut out for you if you were going to get anyone to pay attention. The reason Joule's results finally became well known and accepted in the 1850s, and why today we have an energy unit called the Joule, and not the Mayer, is due to the efforts of one William Thompson, also known as Lord Kelvin, the same Kelvin from which the absolute temperature scale receives its name. Originally a skeptic of Joule's conclusions, Thompson nevertheless began a several-year scientific collaboration with Joule, even writing a joint paper on the Joule-Thomson effect, a physical phenomenon that we use nowadays to liquefy gases. By the mid-1850s, Thomson was convinced that Joule, not Lavoisier, was correct in his model of heat, and the influential English nobleman brought the British scientific community along with him, at a time when the sun never set on the British Empire and the United Kingdom was enjoying worldwide dominance and influence. Hence, despite Mayer's protestations from Germany, Joule ends up getting most of the credit for the relationship between work and heat, and his name is the one best remembered to this day. Even in science, sometimes it's who you know, not just what you know, that makes all the difference. And with that, one of the major scientific theories that had guided discovery for nearly 70 years was abandoned. The evidence was more than enough to show that caloric wasn't a thing, and that mechanical energy and heat energy were both part of overall energy. Both of these observations tie back to Dr. Eyring's principles of models. Given the evidence from Rumford, Mayer, and Joule, we can no longer claim that the caloric model correlates a substantial body of observable material, as Dr. Eyring claims a good model should. Nor can we say that reliable predictions can be made using this model. And even though the caloric theory did suggest important new experiments, by the 1850s, the evidence now required that we change the theory. And this is exactly what happened. First, Rudolf Clausius took the ideas summarized by Mayer and Joule and combined them into what is now known as the First Law of Thermodynamics. There are many statements that summarize this law, such as, the energy of the universe is a constant. You can't get more energy out of something than what you put into it. Or even saying, you can't get ahead, you can only break even. All of these are based on the First Law of Thermodynamics. Mathematically, this law is stated as follows, where du stands for the differential change in U, the internal energy of the system. The squiggly-shaped symbols, called dels, are from the lowercase Greek letter delta and represent inexact differentials, a calculus term referring to the fact that the values of heat, the Q, and work, the W, vary depending on the path of the process, as Mayer had illustrated. The algebra version of the first law we typically use in general chemistry is delta U, that is the change in the energy, is equal to Q, the heat, plus W, the work, showing that the overall change in energy will still remain the same if the initial and final conditions are the same, even if the amounts of heat and work vary due to the conditions of the process. We can equate the effect of the first law to the experience of climbing a mountain peak. There may be many different routes we could use to climb the mountain, but the overall change in elevation, which is the change in energy, will remain the same. This is like Mayer's processes of constant volume or constant pressure, where he had different values of heat and work depending on conditions, yet the overall change in energy, the delta U, is still the same. And I suppose to be fair, we should mention that engineers write the first law as delta U equals Q minus W instead of Q plus W. The change in algebraic sign for work comes from convention, which stems from a point of view difference. For example, when a steam engine is running, are you focused more on what happens inside the engine? That would be the chemist. Or more focused on what the engine is doing to everything else? That would be the engineer. That changes slightly how we view the first law. But we aren't going to worry about that here. We'll just recognize that both work and heat contribute to the overall energy of a system and leave it at that. With the development of the first law of thermodynamics, a new model was needed to give us the molecular picture that could describe how we get heat and work. Remember, a law doesn't explain how phenomena happen at the molecular level. It only summarizes what happens generally. In this case, the first law states that the amount of energy in the universe is a constant. It may change form, but the total energy will not change. We still need something that describes how molecules behave based on that general observation. One thing that helped in developing a model to go with the first law was the molecular level worldview that had taken hold by the mid-1800s. A lot changed between 1789 and 1850. By this point, Dalton's theory of atoms was well known and gaining wide acceptance. Our understanding of things such as the composition of the atmosphere had improved greatly over the decades. And, of course, thanks to first Rumford, then Mayer, and Joule, we now understood that heat was related to motion. So, the theory to replace the caloric theory came to be known as the Kinetic Molecular Theory. Ideas that contribute to the Kinetic Molecular Theory can be traced back to the 1700s. But in the 1850s, Clausius, James Maxwell, and Ludwig Boltzman probably get most of the recognition for its development. Instead of heat being a substance that can flow from one material to another, or that can push apart particles of a substance, this new theory states that heat occurs when energy is transferred from one body to another due to a temperature difference, resulting in a change in the motion of individual molecules. For example, the particles of metal are receiving energy from the molecules of air, becoming faster in the metal. Now, granted, they're not breaking apart, forming a liquid or a gas, but they are vibrating faster within the solid. Then, if we take this piece of hot metal and drop it into a cup of cold water, the molecules of water will receive the energy from the molecules of metal, and the metal particles will slow down on average, and the water particles will speed up on average. Or, if two pieces of metal are rubbed against each other, some portion of the mechanical motion is converted into an increase of molecular motion inside each metal piece, and the result is an increase in observed heat. In this way, we kind of have to recognize that heat is no longer a thing unless energy is actually transferring from one area to another, or one substance to another, or from a reaction to the area surrounding the reaction. We often talk about holding in heat by closing the door to the house, or zipping up your jacket, or putting hot liquid in a thermos. In the kinetic molecular model, though, neither heat nor work exists unless a change is actually happening. For example, if you could perfectly insulate a thermos so that no energy could transfer to the outside, and then added some hot chocolate to the thermos, then the hot chocolate would remain at its initial temperature and never change. The molecules inside the thermos wouldn't have the chance to exchange their energy with the outside world, so their average motion would remain the same, and the internal energy of the liquid in the thermos would stay constant. We often talk about hot chocolate as being hot, but if we want to get technical about it, you can't perceive the hot of hot chocolate unless energy is transferring from the hot chocolate somehow, through the cup to your hand, through the air to your face, or from the liquid to your mouth. You can never really have heat unless energy moves from one place to another. Professor Walter Grandy said, "We still use the phrase heat capacity that connotes an amount of something, although we know better. human perception remains a bit fuzzy in discussing the concept of heat, difficult to pin down at times. Technically, however, we have no trouble agreeing that heat is not a substance, but a process of energy exchange between macroscopic systems and their environments. As our understanding of molecular motion has increased, it has further developed our comprehension of energy in a system compared to the energy of its individual molecules. It was Ludwig Boltzmann, particularly, who suggested that the behavior of individual molecules contributed to the observed behavior of the whole group. He suggested that a statistical treatment of those molecules would correspond to observed thermodynamic behavior. With the advent of quantum mechanics in the 1920s, our ability to describe the energy of individual molecules has improved tremendously and has allowed us to apply Boltzmann's principle at scale to an entire system. The quantum mechanical model can accurately describe the rotational energy of molecules, the vibration of molecular bonds, the behavior of the electrons within the molecule, and even the translational motion of individual molecules in space. Then, using statistical techniques, we can aggregate these energies for a large number of particles, which can now accurately predict the behavior of an entire system of molecules based on the behavior of the individual parts. We call this approach to calculating energy changes statistical thermodynamics, and it has greatly improved our ability to use the behavior of individual molecules to predict thermodynamic behavior in bulk materials. When looking at this new model, the Kinetic Molecular Theory, augmented by statistical thermodynamics, we find that it can explain the data from a set of related experiments, that we can use it to make meaningful predictions, that it correlates a body of observable material, leading to scientific progress. In other words, kinetic molecular theory fits the 4 criteria of a good model outlined by Dr. Eyring at the beginning of this series. We could even say that the kinetic molecular theory also supports the current paradigm of scientists studying energy changes, based on the presupposition that molecules and molecular behavior exist as we currently picture them. We should be careful that we don't find ourselves in the same kind of intellectual rut that scientists appeared to be in during the age of the caloric theory, unwilling to make changes if the data warranted. However, the big difference for us today is that, unlike the 50 years of evidence that proved caloric's downfall, the great discoveries in physics made since 1850, the theory of relativity, the quantum mechanical model, splitting the atom, and new physical phenomena from subatomic particles to vast black holes. All of these developments have supported, not challenged, the laws of thermodynamics and the relationship between energy and molecular motion. Albert Einstein made a famous prediction concerning the laws of thermodynamics when he said, "It is the only physical theory of universal content which I am convinced that within the framework of applicability of its basic concepts will never be overthrown." And that is a bold statement for anyone, even Einstein. At the close of our series, it's a good time to back out and take a 30,000-foot view of this arc of history. We started with Lavoisier devising his caloric model for the transfer of heat. Then we had Rumford, Mayer, and Joule, each challenging that model with additional evidence, until finally the caloric model was abandoned for the laws of thermodynamics and the kinetic molecular model. It is telling and important to note that the actual behavior of matter, whatever it is, never changed during the course of any of these developments. I often mention in my classes a truism learned years ago from one of my own college professors, that atoms will do what they want and they could care less what we think about it. The only thing that changed over the 70-plus years of history we have examined was our mental picture of molecular behavior. not the behavior itself. That behavior remains the same, regardless of our current model, and it will still be the same regardless of how we may change our mental model in the future. We do well to remember that any exploration in the sciences is a search for the understanding of an unchanging truth, and it is a comforting thought that the fabric of reality is not tethered to our understanding. It remains constant as we continually progress in our comprehension, line upon line, precept upon precept, as it were. As former cardiac surgeon Dr. Russell M. Nelson put it, the only thing relative is our understanding of absolute truth. I hope you've enjoyed our journey through the life cycle of a scientific theory or model. By looking at the caloric model, we get a better idea of how a scientific model is constructed, how it functions, how it leads to new experiments and new predictions, and in this case, even how it leads to its own demise and the construction of a new model. Scientific progress is built upon ideas, experiments, discoveries, and the birth of new ideas. And that's a good thing. Thanks for joining us.